Welcome back to the lab. Today we're going to walk through designing a custom battery charger. This circuit is one that we made for our UPS project. For those who may not know, a UPS is a piece of equipment that stores energy for later use and then uses that stored energy to keep electronics running during power outages. A critical part of the uninterruptible power supply is battery management, and when done right, battery management can extend the working life of a battery considerably. Let's dive in. Storing energy has been a challenge for a long time. Throughout history, we've constantly pursued ways to light up the night and use our environment to automate tedious or difficult tasks. This requires energy in one form or another, whether it be chemical energy stored in a combustible fuel, like for a lamp, or gravitational potential energy in weight suspended above the ground, like for a clock. These tasks require energy. Thankfully for us, there have been many generations of people before us. Some of these people have dedicated their life's work to energy storage technologies. Through years of innovation and refinement, we have eventually settled on a few specific types of batteries as great ways to store electrical energy. Batteries store their energy using chemistry, and these use a couple dissimilar metals and an electrolyte to store energy. While these batteries all function through similar mechanisms, some chemistries are more effective than others. Some batteries can be recharged, others cannot. In fact, you could probably make a battery right now with a couple coins and a humble potato. Some battery chemistries are easy to damage. Lithium rechargeable batteries are a bit particular about how they're stored, handled, and charged. Lithium polymer batteries are a great example of this, because overcharging, over-discharging, or physically compromising LiPo cells poses a big risk of causing a fire. This is a real hazard, and if you want to store lithium polymer in your home, like the batteries used in most RC planes and cars, just be careful. It's important to store them somewhere safe, somewhere that if they burst into flame unexpectedly, it can't burn down your house. For me, I have a steel ammo can with a small vent hole drilled in the top, and I use that for storage. The steel will hopefully survive for long enough to contain the fire, while the hole in the top prevents my ammo can from becoming a bomb by allowing the gases of combustion to escape. I mean, it probably wouldn't really explode, but whatever. There are a couple other methods I've seen for LiPo storage, including some sort of fireproof fabric bag, but I don't really trust it, and there's something about a steel box that really just seemed right for containing a fire. Knowing what battery chemistry a charger needs to charge is probably the most important step of making a charger. Different chemistries have some pretty big differences in the way they're meant to be handled and charged. A lead-acid battery charger should never be used to charge a lithium battery. For example, a lithium polymer charger should never be used to recharge a disposable battery. Anyways, we aren't using lithium batteries, so we don't really need to think about that. Consider it a PSA or something, I guess. I suppose we could use lithium batteries, but lead acid is much more common for our application. Why? Well, they're pretty easy to manage for active standby use. They're one of the cheapest battery technologies on the market, and they can provide a ton of current. So they're pretty perfect for a UPS. Before we get too deep into this, I want to start off by saying that I'm not an expert in battery technologies. I understand the requirements for how to safely charge and discharge many battery chemistries, but I don't know the exact detail of how these batteries are constructed, and I'm a bit fuzzy on all the different configurations available for lead-acid batteries. But it doesn't matter a whole lot since the charging process isn't really different between the different tweaks of a lead-acid battery. I'll do my best to cover some of the high-level reasons on why we settled on lead-acid battery management and why we chose a gel cell lead-acid battery for our UPS. Lead-acid batteries don't mind being stored near 100% charge for long periods of time, which is great when we want to use them for active standby use. For a LiPo, it's not the same deal. Actually, lead-acid batteries aren't designed for being cycled. They're made for providing short bursts of power, like for starting a car. If the wrong type of lead-acid battery is deep cycled, it might only survive this abuse for 5 to 10 discharge cycles. There are different subtypes of lead-acid batteries optimized for slightly different things, and these differences have more to do with the way they're physically constructed than anything else. The fundamental chemistry is all the same in these cells, but some optimizations are very important. For example, with flooded lead-acid batteries or automotive lead-acid batteries, It's easy to spill the acid out of the top if it's tipped over. Overcharging or overloading the batteries actually causes the liquid inside of them to boil. What's released out of the batteries is probably just water vapor, but I'd rather not be breathing that in while spilling acid all over my carpet because I tripped over a battery. This is where sealed lead-acid batteries come in. Sealed lead-acid batteries, or SLA batteries, cannot be spilled because they're sealed. These batteries still need to be vented, which allows gases to escape when overcharged or heavily loaded, but all things considered, these batteries don't allow acid to spill out the top, which is definitely a huge plus. SLA batteries don't need to be operated in a particular orientation either, and are generally maintenance-free, but they are more expensive. Now these still have liquid inside of them, or at least most of them do, some of them do. We'll get back to this. Gel cell lead-acid batteries, also known as valve-regulated lead-acid or absorbent glass mat batteries, use a gel to suspend the electrolyte in a paste. Sometimes small gel cell batteries are still called sealed lead-acid or SLA, which is a bit of a misnomer. I guess I'll allow it since they're definitely sealed and definitely won't spill acid onto our carpet. Absorbent glass mat batteries are kind of the bee's knees for lead-acid technology. They use an absorbent glass mat to suspend the electrolyte, which in turn reduces deep cycle aging effects, provides lower internal resistance than flooded or SLA batteries, and can be charged much faster than their counterparts. A big downside here is that these batteries are much more sensitive to overcharging, not to mention more expensive. Since we want to use our UPS in a house where people live, we're going to use SLA gel or AGM batteries. These batteries will provide no risk of spilling acid and are commonly used for commercially available UPS systems. Our battery charger has an adjustable maximum float charge voltage, so we'll be able to tweak the float charge voltage for whatever specific battery we end up putting in the system, but that's no big deal. Speaking of float charging, let's talk about the general charge profile we implemented for a lead-acid battery. Lead-acid has a two-step charge profile. First, a constant current charge mode, which gets the bulk of energy into the battery, but when the battery voltage reaches that final charge voltage, we need to switch into a constant voltage float charge mode. When the float charge current drops below a threshold, we'll cut the charge off and allow the batteries to chill. Okay, that's the theory. How did we implement it? Our charging circuit, as shown here, is fed by a 10 volt 3 amp DC to DC converter. This means that we have 30 watts to play with, and these 30 watts are transformed by a boost converter, which will bring that up to the float charge voltage for our battery cells. We're setting this to 27.2 volts as default from the factory. 27.2 volts equates to 13.6 volts per battery, or 2.26 volts per cell. To prevent exceeding the 30 watt limit for our charging circuit, this means that with the maximum voltage of our batteries put together, we would need to limit our maximum charge current to around 1.5 amps. To decrease charging time to a minimum, we implemented the first charging phase as a 2 amp or 30 watt limit, whichever comes first. The first phase will be both current and power limited. Up to 2 amps or 30 watts will be pumped into the batteries during phase 1. This is being monitored and regulated by one of our processors, which is running a control loop to perform this function. That micro is then responsible for PWM generation, which drives a PMOSFET through the output inductor. This effectively creates a buck converter controlled by software. Phase 2 is where things get different, and this is the float charge. In the float state, the output transistor, Q26, is latched on. This in turn float charges the battery to the input voltage of the charger circuit. This provides a hardware mechanism for preventing overcharge. At very worst, these batteries can be charged up to 27.2 volts. When the software sees that the charge current has dropped below 0.2 amps, it turns off that FET, allowing our batteries to truly float, neither being charged nor discharged. In the future, we may design in a periodic shallow discharge cycle, and this would use the batteries to run the UPS for a very brief time and then recharge them. This might wear out our batteries, might extend their life. I haven't really decided if I like this feature yet, but it also doesn't really matter. We don't need to make this decision today. We can always tweak the firmware for a UPS later and evaluate how it affects the life of our batteries over the next couple years. To allow our microcontroller to make an informed decision about battery charging, it needs to monitor charging current, battery stack voltage, and the voltage of each battery in the 2S stack. Our battery charger is made to charge 2 series, or 2S, lead-acid batteries instead of one battery. This means that there's one more thing we need to consider. Our charging current and power is shared equally between these two batteries. Well, approximately equally, so they're always going to be charging or discharging together. Unfortunately, if our battery's real electrical characteristics are not matched perfectly, one will be charging or discharging faster than the other. Over time, this could mean that one battery is being overcharged while the other battery is not yet fully charged. That's not ideal, since we could be damaging one battery and the other battery isn't even up to full charge. To counteract this effect, we designed our battery charger to control an automatic balancing circuit, and this allows the charge controlling microcontroller to put a light load on whichever battery is reading high, and this naturally requires that we must detect when the voltage on one battery is significantly more or less than the other, but we'll use this information to apply a load, and this load will cause the faster charging battery to charge more slowly, allowing the slow cell to catch up. It does this in our circuit through some transistors that switch a 200 ohm resistance across the battery terminals. For a 12 volt battery, this will cause about 65 milliamps or 0.8 watts of power to be bypassed on one battery or the other. 0.8 watts isn't really a lot, but that should be plenty to bring our batteries back into balance over a long period of time. If the cells get too imbalanced and the circuit can't keep up, we'll add in a restoration routine in the battery charging software, which will drop the charge current down to a trickle while continuing to load the overcharged battery. It'll stay in this state until we force the two batteries back into balance before resuming the normal charge procedure. Our battery charger isn't terribly complicated, but it does require a buck converter that's driven by a microcontroller with a software-defined control loop. This custom control loop allows us to build in some battery monitoring and balancing functions. It allows us to tweak the charge profile of our batteries to extend their life or complete a charge faster. I hope that you enjoyed walking through this modified implementation of a classic buck converter, and for those who have been following this project for a while now, you know that we're coming pretty close to the end. In fact, it's only a few short weeks away. I hope that you're getting excited as we are to see these boards arrive. It's been a long time since we started, but our boards are on order, out for shipping, soon to be delivered. Subscribe to be notified of our future videos where we'll talk about the safety functions designed into our uninterruptible power supply and bring it back to basics by explaining closed loop control using a PID controller. These videos are going to be awesome, don't miss them. I think that this battery charger is a simple and effective charger, which is great. If you think so too, let me know by hitting the like button on this video or leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EEforEveryone, and thank you for staying till the end. Bye!